Okay, so now what we have are two plates that are separated by an oil film that's 0.01 millimeter thick. So we have an oil film here. This is our oil, and the thickness of that is 0.01 millimeters. And the oil has a dynamic viscosity of 0.1 Newton second meter. So let's write that as a given. So it's going to be our mu equals 0.1 Newton second per meter squared. And we know the upper plate is moving at a velocity of 150 millimeter per second. So what this is saying, this upper plate here is moving at a velocity equals to 150 millimeter per second. And we know the oil flow between the plates is laminar with a linear velocity profile as shown in the figure. So here they give us the velocity profile, which is nice. You might not be given it, you might be. So in this case, they give us the velocity profile. This tells us it's always going to be laminar since it's linear. So that's our velocity profile, and what we want to find is the shear stress in pascals at the surface of the top plate. What is this most nearly? So we know here that the velocity profile is going to vary. At the bottom plate, based on the no slip condition, at the bottom, we know the velocity is going to equal to 0. So it's going to be equal to 0 at the bottom because the plate is fixed. So we start at 0, then we gradually, in a linear fashion, increase to a velocity as denoted by these arrows. The velocity keeps increasing until the very top, where our velocity at this point is going to equal to the 150 millimeter per second. So the velocity at this point, at the very top plate, is going to equal to 150 millimeter per second. So that's an important observation for the two plates when we consider this condition of the oil film, specifically for laminar flow. And we also know that the shear stress, which is what essentially we're trying to solve, which is our tau, is going to be provided in the FE handbook, the equation. So I'm going to always refer to the handbook. We can either, I believe, if you look at the fluids mechanics section, you're going to be given this equation. You just take your dynamic viscosity times the velocity gradient. The velocity gradient is our dv divided by dy. So that's our velocity gradient for the shear stress, and this says in the tangent direction. So what this means, to go over some concepts, so if I look specifically at a layer, a single layer in the fluid, this is our layer, we're going to have a shear stress in the tangent direction, tau sub t. And we also have a shear stress in the normal direction. But we're mostly concerned with the shear stress in the tangent direction, and that's what we will solve for. So the shear, here they denote the shear stress in the normal direction. So they use tau sub n, which is going to be our negative pressure. It's going to be the negative pressure at that specific point. So we're looking at a specific point where tau sub n is the normal and tau sub t is the tangential shear stress component. What we're concerned with is the tangential shear stress component. The normal is just going to be the negative pressure, which is stress. It's force per area at that point. But we're concerned with the tangential shear stress when we're looking at the 2D view. So based on that, we know we need the dynamic viscosity, we have the differential velocity, and we have the differential distance. So we can either use that equation, or there's also another equation in the FE handbook. For thin Newtonian fluid film, we know that we can say the velocity varies in the y direction. That makes sense. So as we go up, based on the figure here, if we keep going up in the y direction, we start at 0 at the bottom, the velocity varies until we hit the peak where we have maximum velocity of 150. So we start at 0 and we go up in a linear fashion to 150. and this equals to the velocity times y divided by our thickness of the fluid film. So then we can rewrite this. We take the velocity gradient, which is our differential of the velocity, divided by the differential of the distance, is going to equal to the velocity divided by the thickness of the fluid film. So that's another equation that we can use as well. But the one I will use for this example is going to be this one. So we just take our shear stress is going to equal to our dynamic viscosity times the velocity gradient. The velocity gradient, you can think of it, it's the same as the slope. So it's the slope of the line. So it's the slope at any point. And at any point, the shear stress, when we have a linear velocity profile, the shear stress is going to be the same. The velocity varies, but the shear stress does not change. So that's an important observation as well. So we can use that equation. We take the shear stress is going to be our mu times our dv divided by dy. Again, you can think of this as the slope. It's called the velocity gradient. This is saying as we move up in the y direction, our velocity is going to change. As we move up in the y, the velocity is going to change. It's the slope of that line at any point. And we're concerned here with, essentially, they tell us at the surface. So let's just, we know the shear stress is not going to change. So it's going to be the same at every point as we move in a linear fashion. So the shear stress is going to equal to our mu, which is 0.1 Newton second per meter squared, times our velocity. So the velocity is given to be the 150. So we take 150 millimeter per second. Oh, sorry, you have to convert that to meters. So 150 to millimeters, you just divide by 1,000, or you move the decimal place 3 to the left. So it's 0.15 meter per second. And this is divided by the distance, essentially the thickness, and it's going to be 0. So it's in millimeters, and we have to convert that to meters. So we move the decimal place 3 to the left. So we start here, 1, 2, 3. So it's going to be 0.00001 meters. And we can solve for the shear stress, and I got around 1500 Newton per meter squared, which is the same as 1500 pascals. So that's our answer, and it should be D. And thanks for watching.